Hello everyone, welcome to Algebra Solutions. Let's learn about functions. Observe the following examples. Let A be a set of books. With each book, we can assign a number which gives the number of pages in it. Thus, we have a correspondence, a relation between the set of books and a set P of numbers. Let's see the second example. Here X represents the set of articles in a shop and Y represents the prices that corresponds to the each of the article in the shop. Here again we have a correspondence or relation between the articles and their prices. Let's see the third one. Here n be the set of natural numbers and s is equals to 1, comma 4, comma 9, comma 16, comma 25, and so on. We can say we can assign each natural number to its square, giving a correspondence bit between n and s. Here the s is the set of square numbers. So we can assign each natural number from n to the squares in s. In such a way, there is a correspondence between these two sets. So, all these examples are about functions. So, here each set and the relation between each of each of the pair of sets is nothing but a function. If you look at these examples closely, all of them have properties in common. In each of the above examples, we have two sets, say x and y, and we have a rule that assigns to every member of x and a unique member of y. For instance, in the example 1, we have two sets, x is equals to a and the set of books y is equals to p. Here a is the set of books and P is the set of numbers assigned to each book, which represents the number of pages in the book. And every member A belongs to A is assigned to its number of pages. Say P of A. Here we are writing the number of pages in the book as P of A. Here P is a rule that sends every member of X into a unique member of Y. Such rules are called functions. Here we have two sets. Set A, here let's say this as X. So here we are representing A. A is the set of books. And we have another set which is Y. Here we have P. P represents the number. Here the number is nothing but the number of pages in each book. Here suppose let's say a set have two books, A and B, and here the A book has 10 pages and the B book has 12 pages. So here the relation between A, the set of books, and the number of pages is represented by P of A. Here first one, P of A is equals to nothing but 10, because we know that here in book A we have 10 pages and P of P is nothing but 12 pages. The representation of this relation in this form is known as a function. Let's see the definition. Here, let A and B two non-empty sets. A function f from a function f from A to B denoted by f A arrows to B is a rule that assigns each member of a unique member of B. Here A is called the domain of F while B is called the codomain of F. Here the set of all those members of B that are assigned by the rule F to some member of A is called the range of F. If some members of B are not assigned to A through F, so they are not called as the range of F. The only those members of B which are assigned to A by the rule F are said to be the range of F. The word mapping is used as synonym for function. So here mapping and function both are same. If A tends to B is a mapping and A comma B belongs to F, then we write this assignment as f of A is equals to B. Also, f of A is called the image of A under F. Let's learn about types of functions. Functions are classified as follows: one function or one-to-one or injection function, onto function, which is also known as surjection, into function, one onto function or bijection, inverse function, identity function, constant function, equal function, and composite function. Let's see each one of these. Here, one function, which is also known as injection. Here, a function f from a to b is said to be one function if no two distinct elements of A have same image in B, which means the elements of B should not be repeated in correspondence with the elements of A. Here it is explained mathematically as follows. Here x1 comma x2 belongs to A, where x1 not equals to x2. So f of x1 not equals to f of x2, which means the image f of x1 from B and the image f of x2 from B are also not equal. Or if x1 and x2 the images if the images from B f of x1 equals to f of x2, then the elements from A x1 and x2 are also equal. Here let's see an example. F of f is equals to x comma a, y comma b, z comma c. So here the set A consists of x, y and z as elements, and the set B consists set B consists elements A, B and C. So here x comma a is pair, so x is mapped to A and y is mapped to B and z is mapped to C. So here each element of A is mapped to each element of B. Neither a correspondence or relation is repeated between the elements of A and B. So here this is said to be a one function because no two different first coordinates are associated with the same second coordinates. So here no two elements of A have same element from B. This is said to be the one-one function or injection function or one-to-one function. Let's see another example. Here f is equals to x comma a, y comma a, z comma b. Here the elements in the set A are x, y, z, and in the set B are a comma b. Here from the coordinates we have x comma a. So x is mapped to a and y comma a. Y is also mapped to a and z comma b. Here z is mapped to b. So here both x and y elements from a have same image from b. So here the relation is repeated between the elements of a and b. So which is not a one-one function. Two different elements x and y have same image a. Therefore the function is not one-one function. Let's see the same kind of function verification problem mathematically. Here the function is defined R to R. Here R to R means real to real. So the set A is all the real values and set B is also all the real values. Be defined by f of x is equals to 3x plus 2. Then f is a 1-1 mapping. So let's check this. For consider x1 and x2 are the elements of A. So here x1 not equals to x2 or f of x1 equals to f of x2. These two are the considerations for a one-one functions. Let's take these two considerations. Let's take the first one. Let's assume x1 not equals to x2. So this means no two elements from the set A are equal. So let's see. 3x1 equals to 3x2 not equals to 3x2. So we are applying this function with these elements. So then we are adding plus 2 for this 3x1. We get 3x plus 2 which is not equals to 3x2 plus 2. So this is nothing but 3x plus 2 is nothing but f of x. So here we are using x1 in the place of x. So we can write the function as f of x1 which is not equals to, here same as we are using x2 in place of x. So f of x2. So we get f of x1 not equals to f of x2. So this satisfies the definition of the function, which is if x1 comma x2 belongs to a, x1 not equals to x2, then f of x1 not equals to f of x2. Similarly, let's see the second consideration, which is f of x1 equals to f of x2. Here we have f of x as 3x plus 2. So we are substituting this x1 and x2. So we get 3x plus 1 plus 2 equals to 3x2 plus 2. So here 2 and 2 gets cancelled. 3x1 equals to 3x2 and then 3 and 3. So now we get x1 equals to x2. This also satisfies the function. So this is from these two verifications we can say that f is a one-one function. In this way we can verify a function is a one-one mapping or not. Let's see the other type of function, which is ontofunction or surjection. A function f a tends to be is said to be an ontofunction if f of a, the image of a equals b. That is, f is onto if every element of b, the codomain is the image of at least one element of a, the domain. Here what it says means we have two sets, A and B. From the definition of function, we can say that the set A as domain and set B as codomain. And every element of A has an image from B. So here the image of A equals B, which means all the elements from B should have a correspondence in A. At least one element from A that must have an image from B. Here f A tends to B is an onto. For every y belongs to B, there at least one x belongs to A such that f of x is equals to y. That is f of A is equals to B, which means there must be no element left in the set B. Every element from B should be mapped with the every element of A. Let's see an example to understand this. Here function is given as set of a comma b comma c tends to set of x comma y comma z. So here we can write this as f of a is equals to x, f of b is equals to y, f of c is equals to, also it is given that f of a is equals to x, f of b is equals to y and f of c is equals to y. So we have to say which type of function is this. Here f is an onto function. This is because here z is not the image of any element of a comma b comma c. Here let's say this set is A and this set is B. So we have A, here A, f of A is x and f of B is y and f of C is also y. So here z is left. Z is left. So not the every element of set B are mapped to set A. So this is not satisfying the onto function definition. So we can say this as this is not an onto function. Let's see another example mathematically. Here f of x is given as 2x plus 3. So for an onto function it must be f of x is equals to y. So let's take this. We have y is equals to f of x. Here f of x is given as 2x plus 3. So from here we can write x is equals to, taking this 3 here, y minus 3 by, and this multiplier as divisor, y minus 3 by 2. For every y belongs to R, there is a x belongs to R. This is the definition of an onto function, such that we can say that f of x equals to, here we are substituting this x value in the f of x in the given f of x expression. So we get 2 gets cancelled, y minus 3 plus 3 minus 3 plus 3 gets cancelled and we remained with y. So we got f of x is equals to y. This is satisfied. So we can say that f is an onto function. Now let's see the another classification of functions, into function. Here f a tends to be said to be an into function if f of a, the image of a is a proper subset of b, that is y belongs to b such that there is no x belongs to b, so that f of x is equals to y. That is if and only if f of a subset of b A function f a tends to b is said to be a bijection if it is both 1 1 and onto. Let's see an example. F is equals to x comma a, y comma b, z comma c. Here domain is xyz and codomain is abc. So here no two elements xyz have the same image, and every element of abc there is the image of at least one element of xyz. So f is both 1 1 and onto. Therefore the function is a bijection. Inverse function. Here each b belongs to b and only one element f inverse of b in a. Thus f inverse is a function from b to a. We write f inverse is b to a, hence f inverse is called the inverse function of f. We therefore conclude if f is 1 1 and onto, then f inverse is also a function. If a function becomes a 1 1 function and onto function, then it must be an inverse function. It can also be an inverse function. Let's see an example. Here f a tends to b. Here the set A has 1, 2, 3, 4 and the set B has P, Q, R, S. So let's observe that here 1 is mapped to Q, 3 is mapped to Q, 2 is mapped to R and 4 is mapped to S and P is left alone. Here observe that F is not a bijective because here Q has two images 1 and 3. So this is not a 1 1 function and P is left, so this is not an onto function. So this is not a bijective function. Then we cannot find or we cannot write f inverse. There is no possibility for inverse function. So f inverse of q is equals to 1 comma 3. Q is assigned to more than one element in A. So f inverse is not a function. Thus the inverse function of f does not exist. Now see the identity function. A function f a tends to a is said to be an identity function on a denoted by ia if f of x is equals to x for all x belongs to a. Here the same set mapped to the same set of elements, which is said to be the identity function. If such that x belongs to R, then f is an identity function. In this case, f inverse is equals to x comma x such that x belongs to R, which is also an identity function. So every identity function is its own inverse. So we can say that every identity function is its own inverse, because the inverse function is also same as the function. Now let's see the constant function. Let's see the constant function. A function a tends to b is a constant function if there is an element c belongs to b such that f of x is equals to c for all x belongs to a, which represents that only one element from b is the image of all the elements of a. So here the constant function is a function whose range is a singleton set. So here the range is only single set, single element. Let's see an example. Here f be a relation defined as follows. A set A and set B. Set A has A, B, C, D as elements and set B has X, Y, Z as elements, and here every element from the A set A are mapped to only one element X from B. So this is, we can write this function as f is equals to a comma x, b comma x, c comma x, and d comma x. Here f of a is equals to x, f of b is equals to x, f of c is equals to x, and f of d is equals to x. So every element of a has only image from b. This is said to be a constant function. Now let's see the equal function. Here two functions f and g defined on the same domain D are said to be equal if f of x is equals to g of x for all x belongs to D. In this case, we write f is equals to z. Here, f is a function between two sets a and b, and g is also a function between two sets a and b. Here, the domain a is same for f and g. So let's see an example. Here set A has 2 and 3 as elements and set B has 4, 5, 6, 7, 8, 9 as the elements. Here the function f is mapped between A and B as 2 to 4 and 3 to 9. So this is the function. Let G be a function defined by g of x is equals to x squared, where the domain of G is 2 comma 3. So f and g should have same domain, so we are taking the same domain for this g function, which is 2 comma 3. So observe that the domain of f and g is the same set, and f of 2 is equals to 4. Here we have f of 2 is equals to 4 and f of 3 is equals to 9. So from the given function of g of x, we have domain as 2 and 3. So 2 square becomes 4. So g of 2 is equals to 4 and g of 3 is equals to 9. We see that f and g assign the same image corresponding to the same element of the domain. Therefore f of f is equals to c. Now let's see the composite functions. Here f a tends to b and g b tends to c be two functions. Then the composite functions of f and g denoted by g circle f here, which is g circle f a tends to c. Here f is a tends to b, g is b tends to c. So g of g circle f is a tends to c is defined by g circle f of x equals to g of f of x. So here the element of the element for the domain for the g function is the function, the image of the function f. Here in the product function g circle f, the codomain of f is the domain of g. That is the thing. Here f of x is the codomain of f, function f. So which became domain of the function g. So the domain of g circle f is the domain of f. The domain of g circle f is the domain of f. Yeah, this is the domain. This is the codomain for the f. For function g, this becomes the domain and this becomes the codomain. So the codomain of f becomes the domain of g, and for the function g circle f, domain of f is the domain of g circle f and the codomain is g. So the codomain of g is the codomain of g circle f. Same set. So g circle f of x is equals to g of f of x. Let's see an example. Here a is given as A, B, C, and B is given as X, Y, Z, and C is given as 1, 2, 3, 4. Here the mapping is from A to X, B to X, C to Y, and X to 1, Y to 2, Z to 2, and 3 or 4 are left. Find GOF, G circle F, and its range. Here consider H is equals to G circle F, which is A tends to C. So A tends to C nothing but here A becomes the domain and C becomes a codomain. Let's substitute. Here the domain has A, B, C. So we are taking H of A equals to G circle F of A. So we can write it as G of F of A. So F of A. Here F of A, the image of F of A is X. Here it is F. Here it is Z. G. F of A is X. So here F of A become X. So G of X is 1. So 1. And H of B we can write G circle F of B. G of F of B. Here F of B is also X. So G of X. Here G of X is 1. And now H of C, G circle of C, which is G of F of C. Here F of C is Y. So it becomes G of Y. G of Y is 2. Therefore, the range of H is 1, 9, 2. So 3 and 4 are not mapped to any element of this A, B, C or the domain set A. So the range becomes only the mapped images which are 1, comma 2. Thank you. Follow for more.